In the second lecture over section 8.1, we'll calculate between energy, frequency, and wavelength, then apply those skills to a new problem, calculating the energy we need to knock an electron off a metallic surface. Let's begin. If you've ever gotten a sunburn, then you know that light interacts with matter, sometimes in a very painful way. Absorption occurs when atoms take in light energy from the surroundings. Most often, this additional energy causes an electron to be promoted from its lowest energy ground state to an excited state. When the atom shrugs off that excess energy, emission occurs. Atoms can only absorb and emit light of a particular wavelength corresponding to their unique arrangement of electrons. This gives each element its own characteristic absorption spectrum, just like people have unique fingerprints. For example, we see very discrete bands of light missing in figure 8.5 because the atoms in the outer layers of the sun absorb the light given off by the inner layers. When these atoms give off excess energy as light, they emit lines of the same colors that are missing here. When emission occurs, the electron has to release energy to drop to a lower energy orbit. This energy is emitted as a particle called a photon. In true quantum mechanical fashion, however, you can only observe the light behaving as a wave or as a particle, not as both simultaneously. To understand how photons were discovered, let's start with the experiment where scientists shone a beam of light onto a metal surface in a vacuum. When the light exceeded a minimum energy threshold, electrons were ejected. This is called the photoelectric effect, and the electrons ejected are sometimes called photoelectrons. In further experimentation, it was found that shining a higher energy or higher frequency light does not cause more electrons to be ejected, but those that do leave the surface will do so with greater speed or kinetic energy. Keeping the same frequency of light but adjusting it to a brighter light, recall this means we have higher amplitude waves, will cause more electrons to be ejected. That's the wave theory of light, but it didn't explain the entire photoelectric effect. For this, we have to turn to Einstein's Nobel Prize work from 1921. Einstein proposed that light behaves as tiny individual packets, or quanta, of energy. If this packet of light has enough energy to achieve the minimum threshold, it will knock electrons out of the metal. If you increase the brightness of the light, Einstein suggested that you are increasing the number of light packets, which increases the number of electrons ejected. Building off of the equation E equals h nu, we can quantify the energy needed to eject an electron. We see that the energy of a photon E is equal to Planck's constant 6.626 times 10 to the negative 34th joules seconds, multiplied by the frequency of light in hertz. Combining this with the equation we introduced in the last lecture, we can modify E equals h nu by combining the two, giving us E equals hc over lambda. This means that, given the wavelength or the frequency of light, we can calculate the energy of that light. Let's try some examples. What color is a photon that has an energy of 3.28 times 10 to the negative 19th joules? I'm given energy E, and I need to find the wavelength to determine the color. We can use E equals hc over lambda rearranged to find the wavelength lambda. We know that visible light has wavelengths in the 400 to 700 nanometer range, so we convert meters to nanometers. Referring to our textbook, this falls in the range of what would be considered orange light. This example asks us to calculate the energy of one photon and of 1 mole of photons for violet light. We can calculate the energy of a photon using E equals h nu. This is the energy of 1 violet photon. For a mole of photons, use Avogadro's number. The work function, phi, is defined as the minimum energy needed to remove an electron from the surface of a metal in a vacuum. Each metal will have its own value for phi, and this is a number you'll either be given so that you can calculate the wavelength or frequency, or you'll be given wavelength or frequency and be asked to calculate the work function, phi. Let's look at an example. Here we're actually asked two questions. Given that sodium metal has a work function equal to 3.78 times 10 to the negative 19th joules, we're asked to find the minimum frequency of light needed to remove a surface electron and to calculate the wavelength of this light. Since we're solving for frequency, nu, we'll rearrange the equation and plug in the given values for phi and Planck's constant. This gives us a frequency of 5.70 times 10 to the 14th hertz. Next, we'll use c equals lambda times nu and rearrange to solve for wavelength, lambda. We get a value in meters, but it's customary to report the wavelengths for visible light in nanometers. So let's do that conversion next. Our final answer is 526 nanometers. Remember how I said shining a higher energy, higher frequency light does not cause more electrons to be ejected, but it does cause the electrons to leave the surface with greater kinetic energy? We can calculate how much kinetic energy by using the equation Ke equals Planck's constant times frequency minus the work function for the metal in question. Let's look at an example problem showing how this works. We're asked to calculate the kinetic energy of an electron that is ejected when one blue photon with a wavelength of 472 nanometers strikes a strontium metal surface in a vacuum. To make this work, we need to decide how to apply the equations we've learned so far. We know that we need the kinetic energy equation, but how do we go from wavelength to frequency? Since we need h times nu to plug into our kinetic energy equation, we can use the relationship E equals h times nu, which is also equal to Planck's constant times c over lambda, and knock this out in one big calculation step. Finally, we can use our kinetic energy equation to find out how much of the photon's energy is left over after the electron is liberated from the strontium surface. We see that the amount is small, but equals 6 times 10 to the 21st joules. Note that we lose two significant figures in the process of doing this subtraction. As always, I'll leave you with the parting thoughts of the authors.